we divide by 2, and then we have x squared equals 4. What do we do next? Square root. Good. And we end up with solutions -2 and +2. Those are specific values of x that would satisfy this equation. Whereas an identity, we could basically have all values of x be true for an identity. Okay, so if we take this binomial and square it, regardless of what value of x we put in there, it will be true. This side will equal that side for the specific value of x, which can be anything. Okay, let's just review some of the identities that we already know. Okay, sine theta is opposite over hypotenuse, y over r. Cosine theta is adjacent over hypotenuse, x over r. And tan is opposite over adjacent, y over x. The equation of a circle, or Pythagorean theorem, is x squared plus y squared equals r squared. Those are things you guys already know. Okay, so those should be ingrained. That's 4 identities. You guys already know. One thing that's important is to remember these are called the basic identities. They're the basic identities of trig. Okay, we also know some reciprocal identities. Hopefully you guys have memorized these ones as well. Cosecant is the reciprocal of sine, secant is the reciprocal of cosine, and cotangent is the reciprocal of tan. Okay, I can't remember on your formula sheet. If you guys flip to the back of your book, are these on here, the reciprocal identities?
Yep.
There? Okay. But the basic ones, are they? Or not, are they?
No.
No, so you'll have to memorize these ones, but these ones are given to you. Are you sure these ones are there?
Yeah.
Okay, perfect. So let's just learn how to verify an identity. First of all, what you want to do is look at I'll call it an equation, but it's not. You'll look at the left-hand side of the equal sign, and you'll start breaking that down on the left-hand side. Okay, so you kind of make a little T-chart here, and you'll try and break down the left-hand side, and then on the right-hand side, sine x over cosine x, that will be on the right-hand side, and you try and break that down until you have the left-hand side looks identical to the right-hand side. Okay, that's basically how you would verify. You make sure that the two sides actually equal the same value. Okay, in these cases, this technique does not prove that an identity is true for all values of the variable, but specifically for the ones we're looking at, only the value of the variable being verified. So for example, in this case, we're looking at x equals specifically 60 degrees. If we tried, say, 48 degrees or something like that, it might not necessarily work. Okay, but in this case, let's just prove that it does. So, does tan x in fact equal sine x over cosine x? Well, let's try it. We have tan 60 degrees. We're just going to recall our special triangles. Okay, we're going to prove this algebraically. I see some calculator work back there, which is fine. You'll get the same answer, just not exact. Okay, so for a special triangle with 60 degrees, we have half as our x value, root 3 over 2 as our y value, and 1 as our hypotenuse. So tan we're looking at, we review our basic identity, y over x, opposite over adjacent. So the opposite in relation to 60 degrees is root 3 over 2, and the adjacent is 1 over 2. What's going to happen to the 2's? Good, they cancel out, and what are we left with? Root 3 over 1, which is just root 3. Okay, so tan 60 equals root 3. Let's see if sine 60 over cosine 60 equals the same thing. So using our special triangles again, 60 degrees, sine is opposite over hypotenuse, but our hypotenuse is just 1. So I don't even need that in the calculation. I could just use my y value. I end up with root 3 over 2. That's the y coordinate. Now cosine 60 is adjacent over hypotenuse, so 1 over 2 over 1. But because it's divided by 1, we don't need to show it. Okay, and similar to the left-hand side, these 2's cancel out, and we're left with root 3. So basically we've proven this could be an identity. and it is. I'll just tell you that, okay? That's one of the identities. Okay, and we're gonna verify this identity as well. So tan x squared plus 1 equals secant x squared. But this time it's for 30 degrees. Okay, so tan 30 degrees squared plus 1. Let's break that down. So we need a special triangle of 30. Our x value will be root 3 over 2, our y will be 1 over 2, and hypotenuse is 1. Okay, so if we look at the ratio for tan, it's opposite over adjacent, which means we'll have 1 over 2 over root 3 over 2, all squared, because it's tan 30 squared, and then plus 1. It's going to happen in the 2's. They cancel out. So then we end up with 1 over root 3 all squared plus 1. Now typically we would rationalize the denominator, but because we're squaring it, there's no point in doing that extra step. So 1 squared is 1, root 3 squared is 3, and we have a third plus 1. If you add those together, you should get 4 thirds. Okay, but because we're going to need this skill later, I'm going to get a common denominator of 3, so I multiply the denominator and numerator by 3. So now everything's over 3, and I get 1 plus 3 is 4. So left-hand side equals 4 thirds. Now we have to prove that the right-hand side equals 4 thirds as well. So we have secant x squared, but x is 30 degrees. So secant theta is equal to 1 over cosine theta. But cosine theta is equal to x over r. So what's secant theta equal to? R over x. Okay, we don't have to write all this. Okay, you could have just memorized that secant theta equals r over x. So going back to our special triangle, we have r and we have x. So 1 over root 3 over 2 all squared. Okay, before we square it, I'm just going to clean up what's inside the brackets. Okay, if I multiply by the reciprocal in both the numerator and denominator, I end up with 2 over root 3 squared. Does anyone want me to go a bit slower on how I got that? Going from 1 over root 3 over 2 to 2 over root 3. Is everyone okay? Jump there? Good. Okay, then I'm going to square it. 2 squared is 4. And root 3 squared is 3. So we have 4 thirds equals 4 thirds. Left-hand side equals right-hand side. So we've proven our identity. So a few tips when you're proving an identity and Pythagorean identities. First of all, you have to treat the left-hand side separate from the right-hand side. Okay, well, that means you can never move terms from the left-hand side to the right-hand side or move from right-hand side to the left-hand side. It's on the right-hand side to start, you keep it there. Okay, and another little tip too is never write left-hand side equals right-hand side until you've actually proven the identity. Okay, so you wouldn't start by writing that. So basic identities, those are the ones that are not on your formula sheet and we need to memorize. We're going to use those to prove that tan theta equals sine theta over cosine theta. Okay, now let's just talk about this first. Cosine theta cannot equal 0. Why not? And why would it be undefined?
0 on the bottom?
Yeah. Okay, so if we have a 0 on the bottom, that means it would be undefined because we can't divide by 0. Okay, so cosine theta cannot equal 0 because we cannot divide by 0. Okay, that expression would be, as Mike said, undefined. So let's start with tan theta. Okay, basic identities. Well, tan theta equals opposite over adjacent, so y over x. Nothing else we can do to that. That's the basic identity. Okay, so now let's go to the right-hand side. Sine theta over cosine theta. Well, the identity for sine would be opposite over hypotenuse. And the identity for cosine is adjacent over hypotenuse, x over r. The r's will cancel out, and we're left with y over x. We get the same thing on the left-hand side as we do on the right-hand side, therefore we've proven our identity. Okay, so not only did this work in the last example for just 60 degrees, but it works for any value of x. Okay, so we have proven that using the basic identities. Okay. Now we need to prove that 1 plus tan a squared is equal to secant a squared. And again, we're going to use the basic identities. So first we're going to set it up left-hand side, put a divider, and then right-hand side. So we're creating a T-chart. Let's start with the left-hand side. 1 plus tan a squared. Well, we know that tan a is equal to y over x. I was thinking about other identities, but we need the basic identities. That's what we have to use for this case. Okay, so tan a equals y over x. So we will have y over x squared. And that gives us 1 plus y squared over x squared. Clean things up a little bit, we're going to have to multiply the denominator by x and the numerator by x in the first term to get a common denominator. And when I say x, I mean x squared. Sorry. Okay, so now we have x squared plus y squared over x squared. Is there another basic identity that you guys could find here? Maybe x squared plus y squared equals r squared. So the r squared is now going to replace the x squared plus y squared. And we end up with r squared over x squared. That's the left-hand side. No, they don't. So for example, if you had 4 plus 3 divided by 4, if those 4's cancel out, you get a value of 3. But really, if we added those together, 4 plus 3 over 4, the value is 7 over 4. Are those two things the same? No. So you can only cancel them out if all three terms have a common factor. In this case, they don't. Okay, so you can't cancel out the 4's. You guys have a question on that?
No.
Alright, now let's look to the right-hand side. So we have secant a squared. Okay, so using our basic identities, let's just recall that secant is the reciprocal of cosine. Cosine is equal to x over r. So secant is equal to r over x. We're going to plug the r over x in for secant, and then just recognize that it's squared as well. And then we get r squared over x squared. Left-hand side equals right-hand side, we've proven our identity. Okay, so now we have a few more identities that we're going to introduce. Okay, the quotient identities, so we're dividing to the trig ratio, so tan x equals sine x over cosine x, and hopefully that rings a bell because sine is typically a y, or it is like opposite over hypotenuse. But remember on our unit circle, the hypotenuse is always 1. So sine is like our y, and cosine would be adjacent over hypotenuse, so x over 1. But because it's divided by 1, it's just x. Okay, so by using this basic identity, we're now transferring it to a quotient identity. And I believe this is on your formula sheet as well. You don't have to memorize it, but it's just good if it's quickly, at the front of your brain, you can access it quick. Okay, so tan x equals sine x over cosine x, and then the reciprocal of tan is cotangent, so we're just flipping the numerator and denominator. Cotangent is cosine over sine. Okay, and then we have 3 Pythagorean identities, starting with sine x squared plus cosine x squared equals 1. And that's derived from our unit circle. So do you guys remember the basic identity? Maybe I'll write it this way, y squared plus x squared equals 1. Okay, that would be for the unit circle, the equation of the unit circle. So sine is like y, so we have y squared. Cosine is like x squared. Okay, and equals 1. That's what it's relating to. And it's all derived from the circle equation. Okay, you don't have to memorize these ones either. They're given to you on your formula sheet. So sine x squared plus cosine x squared equals 1. 1 plus tan x squared equals secant x squared. And 1 plus cotangent x squared equals cosecant x squared. Okay, again, they're on your formula sheet. Now these are given to you, but the rearranged versions are not. So for example, if we were to take sine x squared plus cosine x squared equals 1, you could actually rearrange the identities because they're proven. Okay? So if we rearrange to isolate sine, we could subtract the cosine over and get this one right here. Okay? Or vice versa, if we wanted to isolate the cosine, we could subtract sine over, and we'd end up with this one here. Similarly, with 1 plus tan x squared equals secant x squared, if we want to isolate the tan x squared, we would just subtract 1 over, as we see here. Okay, and then lastly, if we wanted to isolate the cotangent, we would just subtract the 1 to the right-hand side, and we'd get this here. Okay, so you can rearrange the identities, and it's good to see its versatility because you will need that when you're proving identities. So next class we're going to be looking at more complex identities, but we're just going to be simplifying a few cases so that you guys are nice and warmed up for tomorrow.
I got scared for a second.
What's that?
You just said like ready for tomorrow, so I was scared you had like a test or a quiz or something.
Oh no, just the next lesson.
Okay. We're okay then.
No stress. Alright, so we have sine x squared over cosine x squared plus 1. We need to write this as a single trig ratio, which means one term, one trig ratio. So right now we have 2 terms. What we can do, there's 2 methods I'm going to show you guys. What we can do first is just come up with a common denominator. So cosine x squared, cosine x squared. Just need to multiply the numerator and denominator to get a common denominator. So from there, we end up with sine x squared plus cosine x squared all over cosine x squared. Okay, but there's an identity, and this is where I want you guys to be looking back to those identities. Do you see anything that can be replaced here? Pardon? Sine x squared plus cosine x squared, that equals 1. Perfect. Good, so now we have 1 over cosine x squared. And Joes, you weren't incorrect, it's just that will be the second way we solve it. Okay. Now we have 1 over cosine. What's the reciprocal of cosine? Secant. So now we end up with secant x squared. one term, one trig ratio, and you're done. So that was method one of how we could do this. Now let's do option 2. So I'll just rewrite what we're starting with. Sine x squared over cosine x squared plus 1. Okay, we have sine divided by cosine. What's the trig identity? Good, we have tan x. But because it's squared, we can write tan x squared plus the 1. Okay, another way, just if you guys are unsure, you could write this as sine x over cosine x squared like that too. Okay, that's a bit easier. It's the same thing. Okay, now do we have another identity? Tan x squared plus 1? Yes, it equals secant x squared. Okay, that's a Pythagorean identity. If you want to just make a note for this one, you can. But hopefully this will just start to develop quickly for you guys. Okay, so the first step, we put sine x over cosine x to tan from this identity.
Why did you square them? Like, or were they?
So I was just showing the class that they were like this, but it can also be written as, say for example, sine x squared and cosine x squared, which would really just be everything squared.
So it's exact same.
Yeah.
Okay.
So it's good to understand that as well in case you see it in different forms.
Okay. Thank you.
No problem. Okay, so we've shown in 2 different ways how to simplify this into a single trig ratio. All right, next one. Sine x plus cotangent x times cosine x. Okay, do you guys see any identities we could use for sine x? Well, we could put it to y over r, but that's going to just make it really complicated. How about we go to cotangent x? Well, we know tan x equals sine x over cosine x. So its reciprocal, cotangent, would be cosine x over sine x. Okay, so we're going to apply that in this example. We have sine x plus cosine x over sine x times cosine x. So when we just simplify things a little bit, we get sine x plus cosine x squared over sine x. Now I'm seeing a cosine x squared, and I have 2 terms. So knowing that I have a sine x in the denominator, if I were to multiply this by a sine x to get a common denominator, I'd get sine x squared plus a cosine x squared, and that leads to our next identity. So you kind of have to be thinking about where are you going. So let's just multiply to get a common denominator now. Sine x times sine x, and we get sine x squared plus cosine x squared in the numerator all over sine x in the denominator. Okay, but sine x squared plus cosine x squared, that's the Pythagorean identity. It equals 1. And we have 1 over sine x. And the reciprocal of sine is cosecant x. And we're done. Just going to show you guys a little bit of work on the side. So if we did use our basic identities, y over r plus cotangent would be x over y, and sine is x. Okay, we get y plus x squared over y. And the r is always going to be 1 on a unit circle, but see how we're running into a little bit of problems? Now we have an r in this denominator, so then we'd have to be multiplying by r's up here. So using our basic identities, it's going to be getting a little bit messier. So think if you can use your Pythagorean identities or your quotient identities, always do that first, because this will just become, I'll go through it. But isn't that looking a little more messy? Probably don't want to deal with that. Okay? It could lead to the same thing. We don't want to deal with that. So please, if you can, use your Pythagorean identities or your quotient identities. So next one, express 2 tan A divided by 1 plus tan A squared in terms of sine and cosine. Okay, and then we have to write that in simplest form. So tan. I've written this out a few times. We know that we can write it in terms of sine A over cosine A. So that's the identity we're going to apply first. So we have 2 sine A over cosine A. And that's in our numerator. In our denominator, we have 1 plus tan A squared. Now, there's 2 ways we could go about it. We could write that it's equal to secant A squared. Or we can write tan in terms of sine over cosine. Mike, what do you want to do?
Secant.
Secant? Okay. So 1 plus tan A squared, just a reminder, that's a Pythagorean identity and it equals secant A squared. So instead of having 1 plus tan A squared, we could just write it as secant A squared. Okay, let's leave the numerator as is, 2 sine A over cosine A, and the denominator. Okay, secant is the reciprocal of cosine, so we can rewrite that as 1 over cosine A squared. So secant A, the reciprocal of secant is cosine. We could write it as 1 over cosine. Why am I doing that?
Oh, so then they cancel.
They will eventually. So the reason why I'm doing this is because we need to write it in simplest terms, and we need it to be in terms of sine and cosine. I'm not allowed to leave this secant.
Okay.
So I have to think about secant and how can I go further? Well, I know it's a reciprocal, and it has cosine within it.
So are you pretty much just trying to like break everything down?
Yeah, and simplify it, like clean it up as best as possible. Okay, so we don't want a fraction over a fraction, so we're just going to keep going. We're going to multiply by the reciprocal of the denominator. And whatever you do in the denominator, you also do in the numerator. So you don't really need to show this bottom step, but I'd like to show it to you because we see that the denominator cancels out. So I'm just going to rewrite what we have. We have 2 sine A and cosine A squared all over cosine A. Now one thing about cosine A squared is it can be written as cosine A times cosine A, right? So if I were to rewrite this as cosine A times cosine A, I think it's just a little bit easier to see that one of these cosine A's will cancel out. So then from there we have 2 sine A, cosine A, and we can call it a day. So cute. Call it a day for that example anyway. Still got a bit more.
Oh.
Um,
Definitely I failed it. what's going on.
So, other skills that will be necessary for next class tomorrow will be the ability to factor trig expressions. So it's important to remember all of our factoring skills, but now apply it to trigonometry ratios. So if you're uncomfortable with leaving the trig ratios within the expression, you could use substitution, so put a variable for sine or a variable for cosine. But I might just try and see if you guys can follow along using just the sign for this one, okay? So what do both terms have in common?
4 at 3.
Well, they're both the power of 4, but what's a term that's in common? It's the leading coefficient on both, so we can factor out a 3. And we're left with cosine theta to the power of 4 minus sine theta to the power of 4. To the power of 4. I wrote 2. Now, do you guys remember difference of squares?
Yeah.
So when we factor the difference of squares, we get conjugates. So 3 will be out front. And conjugates means that we're going to have opposite middle signs. And we have to take the square root of the first term, put it in the front. So cosine x squared, cosine, oh sorry, we're dealing with thetas, so theta squared. And then we take the square root of the back term. So the square root of sine theta to the power of 4 would be sine theta squared. And then we see if we can factor further. But before we do that, identity alert. Just joking. Do you guys see an identity? I just made that up. I just made that up right now. Is this an identity?
Yeah.
It equals 1. I'm going to actually write it. Identity. I can't even spell it right now. Identity. Alert. So now we have 3 times 1 times cosine theta squared minus sine theta squared. But do we still have a difference of squares? Yeah, so we can break down into conjugates one more time. We'll get cosine theta plus sine theta and cosine theta minus sine theta. What are you confused about?
No, I think I got it.
Well, if you take a look at your identities, it's cosine theta squared plus sine theta squared equals 1, not subtraction. So you have to be really, really cautious about your plus minuses. Make sure you're paying attention to that. Okay, can we factor any of these down further? No, so then we're done. We have 3 times cosine theta plus sine theta times cosine theta minus sine theta. I'm going to use that from now on. Just kill Xander. Alright, next one. What's common between the first and the second term?
Sine.
You can go a little higher.
Cosine.
Sine theta squared can be factored out, and we're left with 1 plus cotangent theta squared. Xander, identity alert. Okay, we have an identity right here. 1 plus cotangent theta squared equals cosecant theta squared. I'm pretty sure. Yeah. Double check that for me. Cosecant. Good. Okay, so we have sine theta squared plus cosecant theta squared. And we're going to see, can we simplify this even further?
Yes.
Cosecant is the reciprocal of sine, so we can write this as 1 theta squared, or sorry, sine theta squared times 1 over sine theta squared. And what happens to those signs? Kapow. We're left with 1.